Hi, today we'll be taking a look at linear regression and how to derive the estimators by minimizing the residual, and we're going to do a little Python example as well. All right, so suppose you just have n data points and you want to fit a linear model through it. In this video, I just want to build up an intuition as to where this comes from. So this is our predictor for our model, and b hat 0 is going to be our intercept, and b hat 1 is going to be our slope. In order to estimate this, we have to understand the errors. y1 minus y hat 1 is just the difference between the true value and the predicted value. But actually, looking at errors this way is not that great, because you may have cases where your true value is greater than your predicted value or vice versa. So when you sum up all of your errors this way, if your error is low, that doesn't necessarily mean that your model is performing well, because you may have very large positive errors and very large negative errors, and they just end up canceling each other out. So in order to fix this, we square the errors, and we have an expression, what is known as the residual sum of squares. And this RSS expression is actually just our squared error, the sum of square errors for our model. So the lower this error is, the better our model is. And I'm going to rewrite this in summation notation. So let's minimize this. Well, first observe that it is differentiable, and in order to find the minimum, we will first take the derivative and set it equal to 0. Again, this is our RSS. Taking the derivative with respect to beta hat 0, we end up just applying our power rule and multiplying it by a -1 because we have a -1 in our coefficient of beta 0. We can actually just get rid of the -2. We don't really need it. Now we're going to expand our sums, and we're going to notice that everything stays the same except for this sum of beta hat 0 term. And I just want to make a note that we're summing from I equals 1 to n for all the sums unless it's specified. So because we're summing this n times, all we're doing is going to multiply it by n. And then we want to solve for beta hat 0. That is essentially what we want to do. So I move beta hat 0 and beta hat 0 to the right-hand side, and the left-hand side just becomes what you see on the right-hand side in this expression. Just move stuff around, some algebra. Now I will divide everything by n. When I divide everything by n, when I divide the sum of the yi's, which are n of them, and divide it by n, I am simply taking the average. Same for the x's, which I would denote as x bar and y bar. And awesome, we have derived this b hat 0 estimator. Now we do the same thing for b hat 1 by taking the derivative with respect to beta hat 1. Applying our chain rule, we get a -2 term, and then we end up having there's a 2 multiplied by a negative xi term, because we have a negative xi term in front of the beta 1. And like before, we can just get rid of -2. We don't really need it. And we're going to take the expression for beta hat 0 we derived just earlier, and we're going to plug that in. And this is positive because the second term of our expression for beta hat 0 is negative, so this becomes positive in this case. Distribute the xi's, expand the sums, and notice that because there are two beta hat 1s here, I took out a negative beta hat 1. This is just my choice. So then that means that I will be writing the xi square term first. I'm doing this so that I can just manipulate this equation easier and solve for our beta 1. I'm going to add beta 1 times this expression in parentheses on the right side, and this is what I get. Now I will divide the expression in parentheses to solve for beta 1. And then I just rewrite the sums. Actually, we're not quite done yet. This works, but this is not the form that you will really see. In order to get to the final form that you usually see in your textbooks or elsewhere, we're going to add the numerator to the numerator and to the denominator these sums. We're not really doing anything with this expression except adding by 0. You can quickly verify that this is 0 by looking at the sum, expanding it out, and multiplying everything by n over n. On doing so, I actually want you to try to work out the algebra for yourself and see that this is true. This is what you will normally see in your textbooks and in other materials. So, all right, great. We have derived our beta hat 1 and our beta hat 0. So now let's look at a little Python example where we can apply this. So what is the data we're working with here? So let's suppose we have just some heights and weights, as in the height and weight of people. So we're trying to predict the weight of a person by just looking at the heights. I have used a piece of code, which I will reference in the link below. And this is just simply randomly selecting training, test, and validation sets. And we will have 20,000 training points and 1,000 test points. All this code will be provided in the description below. Once again, this is what we have derived for our beta hat 1 and beta hat 0. So first, I want to use x bar and y bar by using numpy.mean of the height strain and the weight strain. I will first set a variable called num, which denotes numerator, and then denominator. And all I'm really doing here is just replicating this beta 1 expression. And I'm taking beta 1 to be numerator over the denominator. And then the beta hat 0 is just y bar minus beta 1 times our x bar. If you're unsure about what the zip function does, it just means that we are going to be iterating through height strain and weight strain at the same time instead of 2 for loops, so we're not considering every combination. You can look in the zip documentation in Python to learn more. All right, so when we actually do this, we plot our data and we flit our line through it, and we actually have a relative error for a model of 0.06, which isn't too bad. And this is just our plotting. So what I did here was just this PLT plot on the first line is just plotting all the scatter points. And PLT plot on the second line, it is just simply plotting my model. This beta 1 times height test plus beta 0. And then here I am just, the code here just calculates the relative error. Once again, all this will be provided in the description below, so you can run this yourself and take a look. Remember how I said I used 20,000 training points? Actually, if we just use 100 training points or 1,000 training points, we'll get something similar, like this. So this shows that for linear models with very, very few parameters, in this case, we only have one parameter to predict our target variable, we actually don't need a whole lot of training points to make the model work very well. As you can see, the difference between 1,000 and 20,000 is almost minuscule. All right, this wraps up this section for linear regression. Thank you for watching.